NanoHub U, online instruction.
Hey everyone, welcome to lecture 4.4. So in the last lecture, we were just talking about 2D photonic crystal lasers, and now we're going to actually explore what happens when you have an OmniGuide-like structure for fiber laser. And so in this case, you have an OmniGuide here, okay, in this cross-section, and the OmniGuide fiber in the simulation is assumed to be short, okay, because we just want to see, can you generate the fiber laser pulse and then not worry about propagating it through long distance, okay? And so here's basically a picture of what the pump wavelength looks like. And so this pump presumably is outside of the band gap of the OmniGuide, okay? So that's what allows it to penetrate inside of here. But after you've done that, then it's going to re-emit at a frequency, because the frequency was matched to the band gap of the OmniGuide, that will be well confined inside of this OmniGuide. And so that allows us to convert this short wavelength mode to longer wavelength mode with that active medium, right? And so that's analogous to what we had earlier in the 2D photonic crystal case for the laser. And so if you look at it another way, much like what we saw with the 1D Fabry-Perot cavity, you can see that light comes in with like this relatively high wave vector or short wavelength, and then it's regenerated at a longer wavelength, and then it can emit out the other side of the system. So it's fairly consistent with the 1D Fabry-Perot cavity behavior. And then if we think about like putting these materials into OmniGuide fibers, then you can see the final resonance states that we're generating, which I kind of showed you a little bit before, are going to be similar to kind of the basic modes of the cavity. So these are like Bessel functions, and they decay in a radial fashion. And you can see in this case, they have like azimuthal symmetry as you rotate around the cylinder, so in the theta direction. And then if you look at it from the side view, then you can see that active medium is in this corner on the bottom, and then it emits like right out of the active medium into the fiber. And so it's coupling well into the fiber. So that's actually a very nice feature for fiber laser, that you can pump from the side, so you don't need to have optical alignment, but you can have emission down the core of the fiber. And so that's actually very powerful for these kind of fiber laser systems. And then if you look at the transmission that you get from the presence of this OmniGuide, you can actually see that the transmission has been enhanced more than a factor of 1,000. So that shows that even though it's not a very big cavity, this gamma, or effective gain coefficient inside of this fiber, can be very, very large, assuming you have sufficient pumping. So that's a very critical result to show like how strong this kind of configuration can be for fiber laser. And as you may or may not know, fiber lasers are becoming increasingly common form of laser, because they have both relatively reasonable cost and ability to get very high performance. But there hasn't been as much work on generating lasers inside of OmniGuide fibers, but there has been some related work on generating fluorescence and then capturing the fluorescence in OmniGuide fibers. So this is kind of illustrating some of that potential for future work. In the next lecture, we'll actually change gears a bit and start talking about some other multi-physics problems.